So, we have learned how to quantize the free electromagnetic field. In today's lecture, we will discuss the quantization of free fermions. So, let us start discussing. Fermion quantization. What we need to do first is to construct a Lagrangian for the fermion fields, which are Lorentz invariant, and then discuss how to quantize them. Before that, let me introduce you how the fermion fields transform under Lorentz transformation and so on. You are very much familiar with the vector field, which transforms under Lorentz transformation like this. When you perform a Lorentz transformation on a vector field, it goes like lambda mu nu a nu of x. So, let us write down this transformation rule in a fancy way. To do that, you consider this map of vectors in 4 dimension to the following quantity a mu sigma mu, where sigma mu is such that sigma 0 equal to identity and sigma I are the Pauli matrices. So, what you have here is a 0 sigma 0 plus a 1 sigma 1 plus a 2 sigma 2 plus a 3 sigma 3. If you write it in the 2 by 2 matrix form, then what you get is this quantity is simply a 0 plus a 3, a 1 minus I a 2, a 1 plus I a 2, and here a 0 minus a 3. Let me call this matrix as M. So, it has components M, A, B. So, for every vector field in 4 dimensions, you have one such 2 by 2 Hermitian matrix, and also for every 2 by 2 Hermitian matrix, you can associate a vector in a 4 vector in 4 dimensions. You already know the transformation rule for a vector field in terms of these components, the 4 vector components A mu. Now, you can ask exactly the same question: how can you phrase the transformation rule of the vector in terms of the components of this matrix M A B, right? So, or in other words, if you make a Lorentz transformation here, how do the components of this matrix M A B, how the elements of this matrix M A B transform under this Lorentz transformation? So, this is just a fancy way of rewriting this very simple transformation rule for a vector field. We will work it out, it will take us a few more steps. So, M A B is nothing but A mu sigma mu A B, right? That is what is our M A B. What is delta M A B? Delta A mu, we will consider an infinitesimal Lorentz transformation. Lambda mu nu for an infinitesimal Lorentz transformation is delta mu nu plus omega mu nu. So, under this infinitesimal Lorentz transformation, our gauge field delta A mu transforms like omega mu nu A nu. Whereas this delta M A B, which is nothing but delta A mu sigma mu A B, this is omega mu nu A nu sigma mu A B. So, this is the transformation rule, which is not very complicated of course, but what we will do is that we will rewrite this transformation rule in a slightly different notation. Okay. So, what I claim is this quantity is nothing but A nu, or I will call as a rho omega rho tau sigma tau of A B. Okay. I want to rewrite this quantity inside the bracket in a slightly different notation. What I claim is omega rho tau sigma tau of A B is equal to I divided by 2 omega mu nu S L mu nu of A C sigma rho C B plus I over 2 omega mu nu S R mu nu of B C sigma rho of A C. I am yet to tell you what are these SL and SR mu nus. So, SL mu nu is SL I j is nothing but half epsilon I j k sigma k, and SL k 0 is half I sigma k SR mu nu star is minus SL mu nu. So, I told you what are these SL mu nus and SR mu nus, and I claim that if this is how the SL and SR are defined, then I can write this transformation rule for the matrix elements in this fancy way. Okay, this simple transformation rule can be written in such a complicated manner, and then we will see why we are interested to write such a transformation rule. But before that, let me just check, verify that this relation in fact holds. I will do it for one of the cases. Okay, so the point here is that you can look at various coefficients here, omega 0, 1, 0, 2, 0, 3, etc. So you can check whether of omega 0 I or omega I j, they individually match on both sides, both left and right hand sides. So, you can just compare the coefficients. What I will do is I will compare the coefficients, I will compare the coefficients for omega 1 2 for u, and then coefficients of omega 1 2, and then I will leave the rest for you to work out yourselves. So, to do that, what do you need to do? You just take rho equal to 1, okay, and so omega 1 2 will contribute here in the following: omega 1 to sigma 2 of A B in the left hand side, okay. This is your the right hand side is I over 2, and omega 1 2 will appear twice here because of the antisymmetry, omega mu nu and SL mu nu, that will both, if mu equal to 1, nu can be 2, if mu equal to 2, nu can be 1. So, both these terms contribute. So, omega 1 2 times 2 SL 1 2 of AC sigma rho equal to 1, that is what we have taken here, sigma 1 of C B, and then you have plus I over 2 and again twice omega 1 2 SR 1 2 of BC sigma 1 AC. All right, that is absolutely straightforward. So, what you have is I omega 1 2, but SL 1 2 here you can see is just half sigma 3, right. So, this is half sigma 3 of AC sigma 1 of CB, and here similarly plus I omega 1 2 SR 1 2 is just minus SL 1 2 star. So, this is minus sigma 3 of BC sigma 1 of AC, right. There is a half. So, what you get is I over 2 omega 1 2, and this is nothing but sigma 3 sigma 1 of AB in the first term, and in the second term you have a minus, and you can see that the matrix elements are contracted in such a way that it is sigma 1 sigma 3 of AC. The number C here comes. So, this sigma 1 sigma 3, sigma 1 and sigma 3 anti-commute, therefore, this is nothing but twice sigma 3 sigma 1. So, this is I omega 1 2 sigma 3 sigma 1 of AB, which is nothing but sigma 3 sigma 1 is I times sigma 2, right. So, this is just I omega 1 2 times I sigma 2 of AB, which is minus omega 1 2 sigma 2 of AB, all right. This is what we have here, omega 1 2, which is nothing but minus omega 1 2 sigma 2 AB. So, you see that both left and right hand side match. I have to be a little bit careful, this sigma k here, this is sigma k here, and we are considering a metric where eta 0 0 is plus 1, eta ij is minus delta ij. So, you have a minus sign here, you have a minus sign here. All right. So, what you get for the transformation rule here is that under infinitesimal transformation, the vector field transforms like delta A mu equal to omega mu nu A nu, or the same transformation rule you can phrase it in a different way, saying that delta MAB is equal to I over 2 omega mu nu S L all right, because our aim is nothing but A mu sigma mu. So, A mu sigma CB is MCB here, and A mu sigma AC is MAC, the rest all are as it is. So, the finite form for this transformation will be the following. If I define this matrix lambda, or I will call it L of omega AC is nothing but e to the power I over 2 omega mu nu S L mu nu of and I will call R of omega to be e to the power I over 2 omega mu nu S R mu nu. Then the vector field MAB transforms like M goes to L of omega M R transpose of omega. This is how a vector field transforms under Lorentz transformation, or in other words, this simple transformation A goes to lambda A or A mu going to lambda mu nu A nu can be rephrased in this form. Okay. Now that we have learnt this, we can ask individually what do these transformations mean, or in other words, do we have fields which transform under Lorentz transformation in the following manner. Do you have field which goes under Lorentz transformation like what is the notation L of omega psi L, or under Lorentz transformation psi R dagger equal to R omega psi R dagger, and what are these fields called? Huh? Yeah, that's why I took this dagger here. So psi R goes like psi R R omega transpose. Okay. This is known as the left-handed spinner. and psi r is the right handed spinner. Or in other words, yes, indeed there exist fields which under Lorentz transformation transpose in these manners. What are these fields? These are fermionic fields, and we will see why these are fermionic fields, because let us say you consider the left handed field which under Lorentz transformation transforms like this, and then you consider the commutation relation here psi l mij. What is psi l mij? If you just forget about the orbital part, then this is nothing but for an infinitesimal transformation, it is just L acting on psi L, which is half epsilon I j k sigma k acting on psi L, and this m I j is, I mean, it is just epsilon I j k, all right. Therefore, this is just a spin half field. So these, that is the reason I call them spinners. Just a minute. Psi r, all these are two component vectors. Psi r, psi l, both are column vectors. Psi r dagger should have r on the right. Why? The action here comes this way, right? The right action, if you look at this, psi r act, psi l act from the left, and then psi r act from the right. But this is so therefore, the vector field here A mu actually transforms like a bispinner, right? It is because of the presence of both L as well R, it transforms as a bispinner. This is not a surprise, because you can look at the commutation relations. So the Lorentz algebra is just Ji Jj is I epsilon I j k j k, and k I k j is minus epsilon minus I epsilon I j k j k j I k k is I epsilon I j k k k, okay. Or so these j's are the rotation generators and k's are the boost generators, or in other words mij equal to half epsilon I j k j k, and the 0 ith component of the generators M are identified with these k's, the boost generators. Then you can see that the Lorentz algebra just reduces to this. Now what I will do is that I will introduce Ni, okay, which is half Ji minus I ki, and its Hermitian conjugate Ni dagger, which is given by half Ji plus I ki. Then I can look at the Lorentz algebra, and then I can ask what is this algebra in terms of the Ni's and Ni daggers. So let us work it out. So what is the spin half field? I mean, in quantum mechanics, a spin half field under rotation, it just transforms in the following way. Delta psi for a spin half field is just half epsilon I j k sigma k psi. When this happens, it is just a spin half field. Here delta psi is nothing but it is the commutator of psi with the generators of the transformation, right. So you look at the rotation generators. So the rotation generators are just Mij, right. Mij. Now what is my transformation? My transformation is psi L is just L of omega psi L. L of omega is nothing but what is this, e to the power I over 2 omega mu nu SL mu nu acting on psi L. So you look at the infinitesimal transformation here, and because of the definition of psi L, if you remember, SL Ij is just half epsilon Ij k sigma k, right. This is how we have defined absolutely. So this is the definition. So if you look at the omega Ij component of this, it's just half epsilon Ij k sigma k times psi L. That's the reason it's a spin half field. So let's write down the algebra, the Lorentz algebra, the SO3,1 algebra in terms of this Ni's and Ni daggers. What is Ni Nj commutator? It's just 1/4 times commutator of Ji minus I Ki and Jj minus I Kj. Ji Jj commutator is nothing but I epsilon I Jk Jk, and the second term Ji Kj is minus I epsilon I Jk. Ji Kj is Kk, and then this is Ki Jj, okay, this is minus I times Ki Jj commutator is minus I epsilon Jik Kk, and then finally minus minus plus I square is minus, so minus Ki Kj commutator is minus I epsilon I Jk Jk. Okay, this is very straightforward, and then you can see that this is nothing but half epsilon I Jk Jk minus I Kk. So is there a I also? There is an I. So this is nothing but I epsilon I Jk Nk. So what we saw is that the commutator of Ni and Nj just gives you the SU2 Lie algebra I epsilon I Jk Nk. You can check this for the Ni daggers also. Ni dagger Nj dagger will also give you I epsilon I Jk Nk dagger, and more importantly the Ni, Nj dagger, they commute with each other. So what we have seen by this very simple calculation is that the SO3 algebra, SO3 comma 1 algebra is nothing but it is just a 2 copies of SU2 algebra. It is just direct sum of SU2 plus SU2. One of them I will call as the SU2 left, and then the other one I will call it as SU2 right. And you know all about irreducible representations of SU2. I can label the irreps of SU2 in terms of the dimension of the representation. So, a SU2 scalar will simply be denoted as 1, SU2 doublet or as SU2 spinner is 2, and so on. So then accordingly I can have the SO3 comma 1 fields or the irreducible representations of the Lorentz algebra 1 comma 1. So because there are 2 copies of SU2, therefore I will have 2 numbers, 2 integers to label an irreducible representation for the Lorentz algebra. So I will call this as 2n plus 1, 2n prime plus 1, and an irreducible representation of Lorentz algebra can be labeled like this. Just as an example, 1 comma 1 will simply be a Lorentz scalar okay, and 2 comma 1 is a left handed spinner. So I will call this to be SU2L, SU2R, and these quantum numbers denote the transformation under the SU2L and these under the SU2R. So this is just left handed spinner, and these are all 2 component spinners, right? And 1 comma 2 is just right handed you can have 2 comma 2 and so on. This is just what we have seen is that this is the vector representation and then so on. So this is how you can characterize the irreducible representation of the SU2 of the Lorentz algebra. And what we have seen in particular is that we can have, this algebra admits spinor representations. There are these Weil spinners which are which transforms under SU2L as well as SU2R. Now what we can do is we can ask the following question. Now that we know what are the spinners, can we construct a Lorentz invariant Lagrangian which involves these spinners? These are, by the way, also called as the Weil spinner. Okay? So we can have these left handed as well as right handed Weil spinners, and then we can construct a Lorentz invariant Lagrangian or a Lorentz invariant action from these Weil spinners. What we need to do is that we need to keep track of which one is a left handed spinner and which one is a right handed spinner and so on. So we will, what we will do is that we will introduce something which is known as a Dirac spinner, which unlike these left handed and right handed spinners that we have introduced just now, these are 4 component spinners and they do not belong to irreducible representation of the Lorentz algebra. These spinners are, they are some reducible representation, and the Dirac spinner I will call this as psi. A 4 component Dirac spinner is just psi L and psi R. 2 copies of the wild spinner is just one Dirac spinner. So what we will do is that we will consider the Dirac spinner, and then we will see how this Dirac spinner transforms under Lorentz transformation. You already know how psi L and psi R transfer under Lorentz transformation. Therefore, it is not so hard to write down the transformation rule for the Dirac spinner under Lorentz transformation. We will write down the transformation property for the Dirac spinner under Lorentz transformation, and then we will ask, can given this Dirac spinner, can we write down a Lorentz invariant action involving this Dirac spinner which gives us physically meaningful solutions? That is the question that we would like to ask. Okay, so I will just tell you how this Dirac spinner transforms under Lorentz transformation, and then I will close the lecture here, and then tomorrow we will write down a Lorentz invariant Lagrangian involving the Dirac spinner and then its solutions and quantization of Dirac field. So, under Lorentz transformation, how psi L and psi R transforms? Psi L goes to some e to the power I SL mu nu right. So, this Dirac field, no, this is fine. It is just a 4 column, okay. It's, I mean, how do you label is up to you, and then the Lorentz transformation here will, I mean, you have to, you can rewrite the Lorentz transformation if you want to write the Dirac spinner as psi R and psi L, you are free to do that. The transformation property of the Dirac spinner will be written accordingly, okay. So, this here is e to the power I over 2 omega mu nu. I will call this as sigma mu nu, and psi, this sigma mu nu here is nothing but I over 4 gamma mu gamma nu. Gamma mu and gamma nu are known as the Dirac matrices, and the commutator of gamma mu and gamma nu is nothing but the generator of the Lorentz transformation for the Dirac spinners. Gamma mu, gamma nu, etc. are the Dirac. They have the following property. If you look at the anti-commutator of gamma mu, gamma nu, it is just twice eta mu nu. You can find a suitable representation for the Dirac matrices, and then you can show that this transformation is indeed equivalent to this transformation here, which we will do in the next lecture. And then we will show that a transformation of the Dirac spinner under Lorentz transformation like this amounts to saying that the left-handed and right-handed components of the Dirac spinners under Lorentz transformation transforms like this, and hence you know that this, I mean, first of all, this is a reducible representation, and this reducible representation decomposes into 2 irreducible representations. These 2 irreps transform in the following manner. That is what we will do, and then we will write down a Lorentz invariant Lagrangian for the Dirac field and then quantize it.